Hello friends, in today's question, a rectangular solid box of length 0.3 meter is held horizontally with one of its sides on the edge of the platform of height 5 meter. When released, it slips off the table in a very short time t 0.01 second, remaining essentially horizontal. The angle by which it would rotate when it hits the ground will be close to. So we have we can say a platform whose height is given as h, and that is equal to 5 meter, and we have a rectangular blocks whose length is 0.3 and is right at the edge of the table. And as soon as it is released from the table, this box is going to slip and is going to rotate, and we have to find out the angle by which it rotates before it hits the ground. Okay, so in this case, first of all, let's find out the time taken by the box as soon as it falls to reach the ground. So we say time taken by the box to fall to the ground. So we can use the equation S is equal to ut plus half it square, wherein S is the distance, which is equal to h, given as 5 meters, and acceleration due to gravity, that is g, will be equal to 9.8 meter per second square, and initial velocity u is 0, and we say the time taken by this box to reach the ground is given as tf. Substituting values, we get 5 is equal to, this becomes 0 plus half 9.8, and we have tf square. So therefore this tf will be equal to 2 into 5 divided by 9.8 and its square root. Therefore time tf will be approximately equal to 1.01 seconds. So this is time taken by the box to reach the ground. Now it is given that if omega is the angular velocity attained by the box as soon as it starts to fall towards the ground, then we can say, let me write it first, for angular velocity omega, the box as it slips off the table. So under this condition, it is mentioned in the question itself that the box slips from the table, off the table in very short time, that is t is equal to 0.01 second. Okay, so we can write here that box slips off the edge of the table in very short time, and which is given as 0.01 seconds. Therefore we can say that box during this time interval, that is the time is 0.01 second, during this time interval, the edge of the box is still on the table and is nearly stationary. The edge of the box is still on the table, that is, it is nearly stationary. Therefore, now this edge is nearly stationary for a fraction of a second, that is 0.01 second, and the free edge starts to fall. Therefore, we can say that the free edge starts to rotate downward due to gravity. Now we already said that if angular omega is the angular velocity, therefore we can write the relationship that if omega is the angular velocity, so we can say omega is equal to delta theta divided by delta t, where this delta theta is the small angular displacement during the slip time. Okay. During this time, 0.01 second, delta theta is the small displacement. So we can say delta theta is equal to small displacement during time t is equal to point, which is given as 0.01 second. And as the time is very small, that is 0.01 second, so from here we can also say that delta theta will be also very small, such that it can be approximated by using the calculation of acceleration due to gravity and length of the box. By considering acceleration due to gravity and length of the box. Now let us find out the angle of rotation of the box before it hits the ground. Angle of rotation as the box hits the ground. So we can say that after slipping off the table, the box rotates as it falls. Therefore, the total rotation, thus the total rotation by the time the box hits the ground. That can be written as, let us suppose that is given as theta final. This will be equal to omega multiplied by time f, which we already calculated. And for the calculation of angular velocity, that is omega, we can use that as it is going to fall, there will be a force of gravity that will be acting on the center of mass of the box, and that center of mass, that torque will force the box to rotate. Okay. So we can say that the torque due to weight of the box acting at its center of mass, acting at its center of mass. So we can write the equation as torque is equal to mg, and center of mass length is L, so this will be our L by 2. And we can find out the moment of inertia about the edge. So we can find out moment of inertia about this edge, which is just at the, you can say, at about the table. Therefore we can say moment of inertia of the back about its edge, which is in contact with the table. Contact with the table. We can say that our I, which is moment of inertia, will be equal to m L square divided by 3. Therefore, if alpha is the angular acceleration, thus the angular acceleration, which is given as alpha, will be equal to tau divided by moment of inertia. We substitute the values of tau as well as moment of inertia. We get alpha is equal to tau was our mg, and we have L by 2 divided by ml square divided by 3. So mass and mass goes, and this square cancel out with this L. So we get this will be equal to 3g divided by 2L. So this is our angular acceleration. And now we can easily find out our angular velocity. So we can say that angular velocity omega after slipping for the time t is equal to 0.01 seconds. One second. Yeah. So we get omega is equal to alpha t. Alpha is our 3g divided by 2l multiplied by t, and we get 3 into 9.8 divided by 2. Length is given as 0.3 and this is 0.01. So we get omega is equal to 0.49 radian per second. Now we can find out the angle of rotation, which we formula already wrote, that theta final will be equal to omega tf. Okay. You can say the angle of rotation theta final is equal to omega multiplied by tf. Omega is 0.49 and tf we calculated is 1.01 seconds. Sorry. So we can say that this theta f, or we can say final, is equal to 0.495 radians, and this can be approximately equal to 5 because the answer option is 0.5, approximately equal to 0.5 radians. You can say option number C is the correct option. Option C is correct. So this completes the question. Thank you.